So the second talk of this afternoon is given by João Paulo Figueredo, and he will speak about Delphi foliations.
Yes, thank you. Can everyone hear me? Does it sound okay? So that's right. I will talk about the Pezzo foliations. And let me start by giving a motivation. So the main motivation starts with classical algebraic geometry, the study of Fano varieties in algebraic geometry. So what is a Fano variety? Let me remind you. A variety X is called Fano if the anticanonical is positive. So for instance, the projective space and quadratic hypersurface are Fano. More generally, if you take a hypersurface of degree d in Pn, this will be a Fano hypersurface if and only if the degree is at most n. Okay? If you are from the differential geometry context, you'll find this interesting. Manifold is Fano if and only if it has a Kähler metric of positive ridge curvature. So if you want to have intuition about Fano varieties in the geometric point of view, think about manifolds with positive ridge curvature. All right? And another importance is the importance in the birational classification of varieties. So if X has some mild singularities and the canonical is non-pseudo-effective, which means it's not a sequence of effective divisors, then the minimal model program implies that X is birational to a Fano fibration. All right? I'm not being very precise here, but more or less this is the idea. Okay? So Fano foliation can be seen as a generalization of Fano varieties. So let's consider a manifold X. We can also define this kind of foliations on more general varieties, but in our context, in the context of this talk, I only consider smooth varieties and that foliation of rank R. So for any foliation, we can define its canonical bundle, which is only the determinant of the dual of the tangent bundle, the cotangent bundle of the foliation. And you see, if we take the foliation with one leaf, which is the whole variety, this is the case when the tangent of the foliation is the tangent of the variety. The canonical of this foliation is the same as the canonical of the variety. So this is why I say that a Fano foliation generalizes a Fano variety in this sense. All right? So a Fano foliation is simply a foliation whose anticanonical bundle is positive. For instance, if you take X to be the projective space and F a codimension Q and degree D foliation, then you can easily compute its canonical bundle, and you can show that F is Fano if and only if the degree is less than n minus Q. Okay, so Fano foliations are basically, at least in Pn, foliations with small degree. All right? So in some sense, they are the simplest foliations you can consider in the spaces. Okay, so in this sense, as was told by you by Alain in his talk, we can try to classify these foliations because they are the foliations with small degrees. So we can start with the smallest one, which is degree 0. So you know that foliations of degree 0 are always induced by a linear rational map. So this is a classical result. And the next case is this case are the foliations of degree 1. So for codimension 1 foliations, this was classified by Jonulu. And for general rank, this was done by Loray, Pereira, and Tuzé. So there are two cases. Either F is induced by a rational map given by Q linear forms in one quadratic form, or F is the linear pullback of a foliation induced by a global vector field on PQ plus 1. All right? And you can try to do the same for higher degrees. So there are classifications or partial classifications for higher degrees. Okay, so going back to the context of Fano varieties, Fano manifolds, there is a very classical kind of classification result or structure result for Fano varieties, which is called the Kobayashi-Ochiai theorem. So the classical case is the following. Let's go back to a Fano manifold X. And you can define the index of X as being the largest integer dividing the anticanonical in peak X. So that means that minus chi X is equal to Ix times ample divisor. And this Ix is the largest integer that we can choose in this way. So this is positive because the anticanonical is positive. So for instance, if X is a Fano hypersurface, this is wrong. This is n plus 2 minus z. You can calculate the canonical of X and show.
Leave the degree of X.
Leave the degree of X, yeah. So this should be n plus 2 minus z. It's only the okay. So this is minus n plus 1, and this is d. No, this is n plus 2. No? Okay? And the theorem of Kobayashi-Ochiai says that this index is, you can see this in this case, but in general, this index is at most the dimension of X plus 1. And when the equality holds, this holds only if and only if the space is the projective space. So this is one way of characterizing the projective space. These are the only Fano manifolds having the highest possible index. Okay? So it's natural to make the same definitions for Fano foliations. So if you consider a Fano foliation F, we can define the index of F as the largest integer dividing minus kf in peak X. And for instance, if you consider a Fano foliation of degree D in rank R on the projective space, it's easy to see that the index of F is the rank minus D. All right? So, in this context, it's natural to ask if you can find a upper bound for the index of Fano foliations in the same way that happens for the index of Fano manifolds in the classical case. And this was one of the goals in a series of papers by Carolina Araújo and Stefan Druel. And they managed to show this result for Fano foliations. And this is what I'm going to say to you now. So before stating the theorem, let me give a definition. Given a foliation F, we can define its algebraic rank as the rank of the biggest algebraically integrable subfoliations of F. So if you have a foliation, you can consider all the subfoliations, only the ones whose general leaf is algebraic, and you take the biggest one or the biggest rank of all these algebraically integrable subfoliations. This is defined as the algebraic rank of a foliation. And for instance, if you take a fibration from X to S, where X is a threefold Nasa surface, and G a transcendental foliation S, a foliation whose general leaf is not algebraic, then the pullback has algebraic rank 1. The subfoliation is given by the fibers of F. All right? So the theorem, the more general version, is that if F is a Fano foliation, then the index of F is bounded by the algebraic rank of the foliation. Moreover, there is a characterization of the equality. So the equality will hold if and only if the space is the projective space and the foliation is the linear pullback of a transcendental foliation with 0 canonical class. Okay? So, since the algebraic rank is always less than the rank, this theorem will imply that the index of a Fano foliation is always bounded by the rank of the foliation. So we can ask what happens when there is this equality. This is equal to this. So if this is equal to this, in particular, the rank will be equal to the algebraic rank. So the foliation will be algebraically integrable. Okay, so as a corollary of Kobayashi-Chai for foliations, if there is equality of the index with the rank, then the space is Pn. And we know that the index for foliations on Pn can be calculated in terms of the degree of the foliation. And foliations with high index are the foliations with small degree. So the biggest index is the same as the smallest degree. So foliations with the biggest index are the same as the foliations with the smallest degree, which are the foliations of degree 0. So these foliations are precisely the ones classified by Darboux, the foliations of degree 0. So the biggest case are the foliations on Pn induced by linear rational maps. Okay, so this is the first easiest case of Fano foliations. The next one, in order of complexity, are the foliations whose index is R minus 1. So in Pn, this will be the foliations of degree 1. This is what we call the Del Pezzo foliations. So a Del Pezzo foliation is a Fano foliation of rank R, whose index is the rank -1. So on Pn, a foliation will be Del Pezzo if only if its degree is 1, as I said before. So by the classification of Loray, Pereira to Z, the Del Pezzo foliations on Pn are either the ones induced by the Q-linear forms in one quadratic form. So in this first case, this foliation is algebraically integrable. This is given by a rational map. So the leaves are algebraic. Or in the second case, F is the linear pullback of a foliation induced by a global vector field on PQ plus 1. So in general, not algebraically integrable. So we already see that Del Pezzo, unlike the previous case of the highest possible index, Del Pezzo foliations can be non-algebraically integrable. All right? So these are the Del Pezzo foliations on Pn. Pn is a particular instance of a Fano manifold with Picard number 1. Another Fano manifold with Picard number 1 are the quadratic hypersurface. In order of complexity, the next simplest case. So we can also try to classify Del Pezzo foliations on Q1. So this was mentioned in Alan's talk in the morning. So first, if you consider a Del Pezzo foliation on Qn, suppose that this foliation is the restriction of a foliation, transverse foliation on Pn plus 1. So Qn is a quadratic hypersurface on Pn plus 1. Let's suppose we start with this foliation f on Qn. Suppose it's the restriction of a foliation on the whole space. So this foliation is a Fano foliation with maximal index. And this will be easily seen by a kind of adjunction formula for the canonical bundle of the foliation. So the foliation f is Del Pezzo, so its canonical is -r plus -1. And at the same time, by adjunction, this is kg plus 2h. And this will be a plus 2. So this a will be equal to -r plus 1. So this means that a is negative, and the index is r plus 1. So the index is equal to the rank of the foliation G. So G is the Fano foliation on Pn with the highest possible index. So this is a linear foliation, as I mentioned before. Okay, it turns out that all Del Pezzo foliations on the quadratic hypersurface are induced by the ambient space. So the Del Pezzo foliations on Qn are always the restriction of a linear rational map. So the question is, are there any other examples of Del Pezzo foliations? And I will be very particular here when the Picard number of the variety is 1. So the question is that, and let me try to answer this and say that the answer in the case of Picard number 1 is no. These are the only Del Pezzo foliations on manifolds with Picard number 1. Okay. So let's further characterize these foliations. So by this theorem here, if this is r minus 1, then the algebraic rank is either r minus 1 or r, right? if the first case holds, if this is equal to this, that means we have the equality in the Kobayashi-Ochiai. And by the theorem by Araújo-Druel, this will mean that the space is projected space, and F is a linear pullback of a transcendental foliation on P n minus y plus 1 with zero canonical class. Okay? If the other case holds, this will mean that the foliation is algebraically integrable, since the rank of the foliation is its algebraic rank. So this means that if you start with a Fano foliation and suppose that the space is not the projected space, this will imply that this first case cannot hold, so only the second case, and this implies that F is algebraically integrable. So the Pezzo foliations, in all cases except the one was classified by Loray, Pereira-Tuzé, have algebraic leaves. All right? So we can consider these leaves. So let's consider a general leaf, take its closure inside X, and take its normalization. Let's call this map, this N from F to X. So this F will be the normalization of a closure of a general leaf of the foliation. So since this is a leaf, if you restrict the canonical of the foliation to this F, this will be Kf plus delta for some effective veil divisor on F. This pair, F delta, is called the general log leaf of F. So if F is Fano, this means that this Kf is negative. Its pullback will also be negative, so this will be negative. This Kf plus delta will be negative, so the pair F delta will be a Fano pair. So this is a very nice characterization of the leaves. So if the foliation is Fano, its leaves are of Fano type, if they are algebraic. So we can also define the index of a Fano pair, more generally than the index of a Fano manifold. And in this case, the Fano pair will have index the dimension of the leaf minus 1, because this is R, the dimension of the leaf is R. So the index of the Kf plus delta is the same as the index of the canonical of the foliation. So this pair will be a Del Pezzo pair. And it happens that there is a classification of log canonical Del Pezzo pairs by Fujita. So we classify all these possible log leaves if the singularities are log canonical. More generally, Carolina, she managed to remove this log canonicity hypothesis, and she gives a list of all the possible F deltas. I will not give all the cases, but some cases are PR delta 2H, QR 8, and another one SC, where S is a Veronese surface. So it's the image of the Veronese map from P2 of degree 2. And C is an element here of degree 1. And in total, there are 7 classes. Okay? Another aspect which will be important is the following. If F is, in general, if F is an algebraically integrable foliation, it's not necessarily true that if you take the closure of the leaves, they will meet at one point. But this will be true for Fano foliations with log canonical singularities. And this is a result by Carolina and Druel. So for algebraically integral Fano foliations with log canonical singularities, there is a common point in the closure of the general leaf. So all these log leaves, we have a classification of them, and moreover, we have the effect that they all meet generally in one point, at least one point. So this gives a lot of geometric information on the spaces itself, and this will be enough to show that in the case of Picard number 1, this only happens if X is the Pn or Qn. So how do we do this? We consider families of rational curves. So given a variety, we can consider the normal scheme parameterizing rational curves on X. So a family of curves will be only a reducible supervariety of this normal scheme. And we have this lemma. If X is a Fano manifold with Picard number 1, and H a family of rational curves with dimension m and degree given by the anticanonical polarization D, such that all curves of this family pass through a fixed point X, and some curve of H is free, meaning it covers X, this will imply that the index of the Fano manifold is at least m plus 2 over D. So this gives a bound of the index of Fano. So if this bound is big enough, this will imply that X is easy to describe. So how do we do this? As I mentioned, we can suppose that X is not Pn. In the case of Pn, you have a classification by Loray Pereira Tuzé. So if X is not Pn, F has algebraic leaves. We use the classification of the all possible leaves. In all these cases, we can find families of lines inside these leaves, except in one case, which is the Veronese surfaces. The case of the log leaf is a Veronese surface, but in all the other cases, we can find lines, so degree 1 rational curves. And we can also use the fact that the leaves meet at one point. So we find families of lines meeting at one point, and we can use this lemma to bound the index of the Fano manifold. So in the case where we don't have the Veronese surface, which will happen always when the rank is at least 3, we can build family of lines passing through a fixed point. So when the Picard number is 1, this will give a lower bound for the index of the Fano manifold, as shown here. This will be the bound. The degree here will be 1. And we can also explicitly calculate this degree m of this family of lines. The case of Picard number greater than 1, I will not talk about this here, but Araújo and Duell shows that if this happens, X is a projective space bundle, and the rank is at most 3. And so here there is a classification, but I'm only concerned with the case Picard number 1. So in this case, applying the previous lemma, we can show that the index of the foliation is at least dimension of X minus 1. And for these Fano manifolds of Picard number 1, we have a classification. So we just need to show, to characterize Fano del Pezzo foliations on these Fano manifolds. So what are the cases? If the index is dimension of X plus 1, then X is a projective space. We are rolling out in this case. If the index is X, then X is a quadratic hypersurface. We already show this, the classification here. If the index is the dimension minus 1, then X is a del Pezzo manifold. And there is a classification of del Pezzo manifolds, as I mentioned before. And it turns out that in this last case, if X is a Del Pezzo manifold with Picard number 1, then X has no Del Pezzo foliations. And how do you show this? We just show, you just consider the list of all these possible manifolds, and for each manifold in this list, you show it's not possible to have a Del Pezzo foliation. All right? So we conclude that if X is a Fano manifold with Picard number 1 with log canonical singularities and rank at least 3, then either X is the projective space or the quadratic hypersurface. And in conclusion, the classification of log Del Pezzo foliations with rank at least 3 is the following. Either X is a projective space bundle, or X is Pn, or X is Qn. All right? So these are some of the references. This is where I prove this theorem. And these are the previous 2 papers where I based all my results. Okay? Thank you.